Velocity, which we looked at in the last lesson, is one example of what we call a rate. And a rate in general can be defined as something that relates two different units, how one unit is changing in terms of the other unit. The most common rate that we're going to be looking at is time. So things for a certain amount of time. So how many centimeters per second, or how many cubic millimeters per second, or something else like that, how many degrees per second. So what we're going to be looking at is problems where you have one rate and you are relating them to a different rate. So we solve these related rates problems by, number one, finding the relationship between the variables and write an equation. Okay. Number two, differentiate both sides with respect to time. So we're going to take d, whatever variable dt, which means we are likely going to have to use the chain rule because time is unlikely to be one of the variables we're actually looking at. And then 3, we're going to substitute in any given values. And solve for unknown. Okay, so example 1. Air is being pumped into a spherical balloon so that its volume increases at a rate of 90 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 300 millimeters? Okay, question mark. Okay, so we're pumping air into a spherical balloon so that the volume increases at a rate of 90 centimeters per second. How fast is the radius of the balloon increasing when the diameter is 300 millimeters? So the very first thing we notice is that we have units that are different. We have centimeters cubed and we have millimeters. Luckily, millimeters is fairly easy to translate into centimeters. So we will need to make sure that we do that. So I'm just going to put a little star there. So the very first thing we want to do is write down an equation that relates diameter. We're looking for actually the radius. We know the diameter. We're looking at a rate of 90 centimeters cubed per second for volume. So we're looking at volume and radius. How can we relate them? We have a volume equation. So the volume of a sphere is 4/3 pi r cubed. Okay, now we're going to go and we're going to try to list out our knowns. So we know that the volume has a rate of 90 centimeters per second. The volume increases at a rate of 90 centimeters cubed per second. So 90 centimeters cubed, whenever we have a rate, this is going to be d something dt. 90 centimeters cubed per second is equal to, and what is the thing that is changing? The volume. So this is dv dt, derivative of the volume with respect to time. Okay. We also know, we're looking at what the diameter is equal. So the diameter equals 300 millimeters, which is divided by 10, 30 centimeters. The radius, we're trying to figure out how fast the radius is increasing. We don't really care how fast the diameter is increasing. So the radius is half of the diameter, which is 15 centimeters. Okay, so now we have to go. So we've got an equation relating the variables. Now we're going to differentiate both sides with respect to time. So we have dv dt equals 4/3 pi times 3r squared dr dt. We're using the chain rule here because we're differentiating with respect to time, not with respect to r. Okay, so we can cancel these 3's here and simplify a bit. Okay, so let's now go back and we have dv dt equals 4 pi r squared times dr dt. We're trying to find the rate at which the radius of the balloon is increasing. That's going to be dr dt. That's our unknown. We know what the radius is. It's 15 centimeters at the point we want it. And we know what dv dt is. It's 90 centimeters cubed per second. So we're going to substitute these in. Okay, so we have 90 equals 4 times pi times 15 squared times dr dt. Okay, so we get 90 equals 15 squared is 225 times 4 is 900. 90 equals 900 pi times dr dt. And we get 90 over 900 pi is dr dt. Simplifying, we get dr dt equals 1 over 10 pi. What unit will we use? Well, we had here with the 15, this was centimeters, so we have centimeters squared. This is centimeters cubed per second. So if we're going to be dividing by 900 pi centimeters squared, and we have centimeters cubed per second, our final unit is going to end up being centimeters per second, which is exactly what we want because that's how the radius will be changing, is in centimeters per second. So the rate of change of the radius with respect to time, this is a common abbreviation, so you might see that as with respect to time. So the radius, we don't actually want to write the rate of change. We're just going to write the radius is increasing at 1 over 10 pi centimeters per second. Okay, so the rate that we are increasing at is 1 over 10 pi centimeters per second. Okay, let's look at a slightly different example. So that's kind of a geometry type problem. Here is a problem that's going to relate a little bit more to the coordinate plane. So a 9 meter ladder is leaning against a vertical wall. It is sliding down so that the bottom is sliding away from the wall at a rate of 0.5 meters per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet. Let's go 6 meters. I'm not going to make you do that conversion. 6 meters from the wall. Okay. So let's draw a picture here to represent this relationship. So we have a 9-meter ladder leaning against a vertical wall. It's sliding down, so the bottom is sliding away from the wall at a rate of 0.5 meters per second. So we're measuring how fast the bottom is sliding away from the wall. Now we want to know how fast the top of the ladder is sliding down the wall at a certain point. Okay, so let's take a look here. We have a wall and we have a floor, and we can assume the wall and the floor make a 90-degree angle. So we have a ladder, and it's in this position, perhaps to start somewhere along here. Let the distance the line is down the wall be y, and the distance it is along the wall will be x. Okay, and this is 9-meter ladder. That's going to be a constant. So at some further point, we're going to have a y that's changed because the ladder is sliding down, and an x that's changed. And if we want to know the rate, what we're looking for is dx dt or dy dt. So if we look up, let's see if we can first write down an equation that relates x and y. So we have a right-angled triangle. We can use the Pythagorean theorem. We know that x squared plus y squared equals 81. Now I'm going to take the derivative with respect to t. So 2x dx dt plus 2y dy dt equals 0. Okay? So what we want to know is, now let's go up and look at which variables we know. Sorry, for some reason I wrote that very wonky. This should be 2y dy dt. Okay. So we have the first piece of information. We have the 9-meter ladder we've already put in. It is sliding down, so the bottom is sliding away from the wall at a rate of 0.5 meters per second. So the bottom is sliding away from the wall. So that is the rate that this is sliding away from the wall. So how fast it's sliding away from the wall is going to be dx dt. So dx dt is 0.5 meters per second. Okay. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 meters from the wall? Okay, so the bottom of the ladder is 6 meters from the wall, so we have x equal to 6. So x is 6. And y, well, we know that 6 squared plus y squared, we can use our Pythagorean again, equals 81. So y squared equals 81 square root. Y squared equals 81 minus 36. So y squared is 45, which is equal to 3 radical 5. Take out that 9. Okay, so now we have dx dt, x, we have values of dx dt, x, and y to plug in. Okay, so we are going to go ahead and rewrite these. So we have 2 times 6 times 0.5 plus 2 times 3 root 5 times dy dt equals 0. Okay, rearranging, we've got a 0.5 times 2 is just 1, so we've got a 6. We're going to move it to the other side of the equation, so we have a negative 6 when we subtract. Simplifying here, we get 6 root 5 dy dt is equal to negative 6. Dividing, we get dy dt equals negative 6 divided by 6 root 5, which is negative 1 over root 5, more properly rewritten as negative root 5 over 5. Okay, so now we're going to answer our question, which is the height of the ladder on the wall is decreasing at a rate of root 5 over 5 meters per second. Okay, and it may seem strange to you that the rate at which it's moving on the bottom is not the same as the rate at which it's moving on the top. But as you can see, when we take the derivative, if we have x squared plus y squared equals 81, the change dx dt, dy dt are going to depend on x and y as well as the speed at which the other one is moving. So it also depends on what the current values of x and y are. So how far it's sliding down the wall is going to change how fast it's moving in either of the directions. Okay. Last example, and this one is definitely a fun one because we get to do some trig. Okay. So example 3. A man walks along a straight path at a speed of 2 meters per second. A searchlight placed on the ground 15 meters from the path is kept focused on them, or on him rather. So the searchlight is following the man. At what rate is the searchlight rotating when the man is 10 meters from the point on, and let's just clarify that he's 10 meters past the point on his path that was closest to the searchlight. Okay, so let's draw a picture of that. We have a beautiful searchlight that's shining light, and the searchlight is rotating. So where the searchlight is, we have a path that a person is walking on. The searchlight is 15 meters in a straight line distance from that path. The person is walking along this path. Let's see if I can draw a reasonable person. Beautiful. Okay, so the person was walking along this path. Okay, so when the person is 10 meters away past the point that is closest to the searchlight, we want to know at what speed the searchlight is rotating, so what rate. So how do we give and define a rate of rotation? Well, we're looking at how the angle is changing. So all we can say to say how fast something is rotating if it's not actually moving is the change in the angle versus the change in time. So we're going to let this angle be theta, and we're going to be looking at how theta is changing with respect to time at the moment where the man is right here. Okay? So let's define some variables. Okay? We have x. That's the direction the man is moving. That is a variable because he is moving. At this point, x is equal to 10 meters, but we have to think of x is changing. So we're thinking about how x is changing. We want to know as x changes, how is theta going to change? So let's see if we can write an equation. Well, this is a right angle because the shortest distance between a searchlight and a path is going to be at a 90-degree angle. So we have a right-angled triangle, we have an opposite side, and we have an adjacent side. So this angle to this angle, we're going to write an equation involving the tangent. So we have tan theta, tangent of the angle, is equal to x over 15, using our right triangle trigonometry, opposite over adjacent. Okay? So we are going to take the derivative with respect to time. Okay, so d tan theta dt equals dx over 15 dt. So we're going to take the derivative there. So we get secant squared theta d theta dt equals 1 over 15 times dx dt. Because again, we have to use the chain rule. So now, what do we know? Well, we know d theta dt is the variable that this is our variable we're going to be finding. We know dx dt. So let's actually just shrink this down a little bit and go over here. We know that dx dt equals, it says he's walking at a speed of 2 meters per second, so dx dt is 2 meters per second. We know we don't even need to plug in an x. It actually doesn't matter where x is, it seems, that d theta dt maybe is only going to depend on how fast the person is walking and not depend on where they are. That's pretty cool. But we do need to know what secant squared of theta is. Huh, interesting. How are we going to figure that out? Okay, well, let's do a little side problem here. I'll make a little box. So secant squared of theta, I don't really have a lot for it, is 1 over cosine squared of theta. Okay, cosine theta is adjacent over hypotenuse, so that would mean secant squared theta is hypotenuse squared over adjacent squared. So we flip it and we square it. So if I want to figure that out, well, let's see how we can find hypotenuse squared. So we know that the hypotenuse squared equals 10 squared plus 15 squared, again by our lovely Pythagorean theorem. So h squared equals 325. The adjacent squared, so the adjacent side to our theta, is 15. So this is going to be 15 squared, which is 225. So our h squared over a squared is going to be equal to 325 over 225. Dividing by 25, we get 13 over 9. So secant squared of theta for this particular triangle is equal to 13/9. So I can plug that back in. That was quite a fun little side adventure in right triangle trigonometry using inverse trig functions. Sorry, not inverse, reciprocal trig functions. So now we have 13/9 times d theta dt equals 1/15 times 2. Simplifying, we have an 18 on top, a 15 times 13 on the bottom, but we can cancel a 3, leaving us with 6 on top, and then 5 times 13, or 65. So d theta dt equals 6 over 65 radians per second. Okay. So how do we know it's radians per second and not degrees? Well, all of the calculus stuff that we've been doing relies on the fact that we're using radians, which are numbers. So if we're actually going back and solving for something like a d theta dt, we are assuming that that what we are using are radians.